Welcome to Chemistry at Hondiga High School. I'm Brian Brown, and today we will be looking at our third set of notes over Chapter 4, where we're going to be getting into Section 4.3 about how atoms differ. Now, at the same time where we were talking about these various experiments in the previous set of notes, other experiments were happening that were shedding light on it as well. And one important contribution was by a scientist by the name of Moseley in 1913, and he discovered that each element had a unique positive charge in their nuclei. Now, that subsequently, years later, when we discovered, oh, they were protons and understood the atomic nucleus better, we knew that that meant each element had different numbers of protons. And that's what made fundamentally boron different than carbon, different than nitrogen, is they each had a unique and specific number of number of protons. Now, that later became known as the atomic number. Now, atomic number then stands for the number of protons. So if you look at the periodic table, find an element, find its atomic number, you know exactly how many protons are in that substance. Now, since atoms are neutral, so whenever we talk about an atom, we're actually talking about a neutral atom. That means our number of positives must equal our number of negatives. So for a neutral atom, remember this doesn't work for an ion, then something different's going on. We'll look at that a little bit later. If we have an atom, then it's neutral and the protons equal electrons. So here is a picture of an element off a periodic table, and the key says that 17 is the atomic number. So how many protons? Well, that must mean we have 17 protons. And if we're talking about atomic chlorine, that would mean we also have 17 electrons. Now, 1910, same general ballpark a few years earlier, Thomson, who's the same guy who discovered the electron, discovered that neon consisted of atoms with two different masses. So we knew it was neon. We knew it behaved like neon behaves, but all neon atoms are supposed to be the same by Dalton's atomic theory. And what he discovered was that was a part of the theory that was not true. So he knew he had neon, but he knew while they were chemically identical, physically they weighed different amounts. Well, why? Well, he discovered the concept of isotopes. Isotopes are atoms with the same number of protons, but different numbers of neutrons. So an isotope of an element would be the same number of protons, so the same element, but having different numbers of neutrons in its nucleus. So if you took a look at, let's pretend we could count what was inside a nucleus, and let's say we had this substance on the left, which we're going to call neon 20. The purples with a plus, those would be the number of protons. So inside neon 20, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 protons. Now, how many neutrons? Well, those would be the neutral charge things in green here. We count through those and we see, oh, the one on the left, it also has 10. But now our other neon, which weighed differently, it happened to weigh more, it still had 10 protons in its nucleus, but it turns out the reason it weighed more was it had 12 neutrons in its nucleus. And you can see how we actually use the total number of particles in the nucleus to describe these two nucleuses. So the one on the left we call neon 20, and the one on the right we call neon 22. And that's something we're going to end up using more of in a second. It's one of our ways in which we have describing a specific isotope of a specific element. Now, if not all atoms of an element are identical, how can we actually then tell them apart? Well, we had to come up with a way of describing different substances. And what we use is the mass number. And the mass number stands for the total number of particles in the nucleus. So it's an actual number, which is why we call it the mass number. Now be careful. Don't confuse this with atomic mass. What we're talking about with mass number is the total number of particles in the nucleus, which would be our protons plus our neutrons. And it's not listed anywhere on the periodic table. What's on the periodic table is atomic mass, not mass number. Atomic mass is a mass that they're describing. Mass number is a number that represents the number of particles in the nucleus. So why did they call it mass number? Well, that's something we'll actually get into in our next set of notes. That the actual mass number is pretty close to the mass of the atom. So if you take a look at these two different types of lithium, the one on the left has a mass number of 7. The one on the right has a mass number of 6. So we would describe the lithium on the left as lithium 7. We would use its mass number, which is unique and different than lithium 6, which has a mass number of 6, to actually differentiate between these two different types of substances. Now, if we put together what we've been talking about, are parts of the atom rules that you're going to be using on the test as well as on your homework is remember one, atomic number tells us the number of protons. So if we know the number of protons, we know the atomic number. If we know the atomic number, the number of protons, we know the element when we look at the periodic table. And now remember also in a neutral atom, the number of protons equal the number of electrons. And unless we have an ion, we always have neutral atoms. And then finally, the mass number would equal the number of protons plus the number of neutrons. Those are three key important ideas for when we are looking at parts of an atom. Now, how do we actually describe different atoms? Well, we have to have a notation that gives us a unique way of describing each element. Now, the one we've actually seen before, we just didn't give a name to it. It's called hyphen notation. So you say the element name and then hyphen and then a mass number, hence the name hyphen notation. Now, I've never seen a book that actually calls it that, but that's pretty much what all of us chemistry teachers call it. So an example, if we say something is potassium 41, we're describing a very specific isotope of potassium. Now, how many protons? Well, here's where we need a periodic table. Unless you've memorized all of the atomic numbers in the periodic table, we need to look up potassium, find it on the table, and then copy down its atomic number, which turns out to be 19. Now, since this substance is neutral and has no charge, that means we also have 19 electrons. So how do we get the number of neutrons? Well, remember, this is potassium 41, and 41 stands for the mass number. Well, if we take the mass number and subtract from that the number of protons, we're going to be left with the number of neutrons. Let me write that a little bit better. So that's the simple formula to use. Mass number is protons plus neutrons. So the mass number minus the number of protons has to be the number of neutrons, which in this case, 41 minus 19 is 22. Now, what's another way of showing that exact same information? Well, we use what's called the symbol notation. Now, symbol notation is much more descriptive, so this tends to be what we use when we're drawing or writing it in a book or I'm drawing it on the board. In the upper or in the middle, I'm going to put the symbol, hence the name symbol notation. Upper left-hand corner, I'm going to put the mass number, and the lower left-hand corner, we're going to put the atomic number. So what would potassium 41 look like in symbol notation? Well, the element potassium has a symbol of K. And since it's got a mass number 41, that's what we'd put in the upper left-hand corner. And its atomic number 19, we'd put that in the lower corner. Now, this is very descriptive, and we don't need a periodic table to describe the particles inside potassium 41 written this way. But it's really hard to pronounce, and it's really hard to type. So that's really where this type of notation comes in. When I'm pronouncing a specific isotope, or I'm typing it in for a test, it's really easy to do it that way. So that tends to be how we use it in those two situations. But if we had it like this, what is the number of protons? Well, atomic number is protons. It's right there. So I can look up here and I can see, oh, it's got 19 protons. How many electrons would it have? Well, this is a neutral substance. And I know it's a neutral substance since up here I don't see any charge written. That means it is neutral. So I know that that also means I have 19 electrons. And then the one nice thing about symbol notation is we can just subtract right down the side. So our math is right there in front of us. 41 minus 19 is going to give us our number of neutrons, which is 22. So these are both the same way of describing the exact same isotope. So let's try a few of them. So we're going to calculate the protons, electrons, and neutrons for each of the different substances. So first we have symbol notation, chlorine 35 over 17. Well, protons, they're right there, remember. Lower left-hand corners are protons. It's got no charge, so that's our electrons. 35 minus 17, it's 18. From the symbol notation, it's quick and easy to determine these. So let's try another one. Calcium, and in this case, its atomic number is 20. It's neutral, so electrons are 20. 41 minus 20, this one's got 21 neutrons. So this would be what we call calcium 41. Hyphen notation. A little bit more work because now we need a periodic table unless you've memorized that iron is atomic number 26. Well, it's just as easy to look, well, it's significantly easier just to get a periodic table, find iron, it'll say atomic number is 26. This is neutral iron since it's not an ion of iron. So that means it also has 26 electrons. And now we've got to do 56 minus 26, 30 neutrons. Something like oxygen 18. Since it's oxygen, I know atomic number 8, so it's got to be 8 protons. It's neutral, 8 electrons. And 18 minus 8, Means I have to have 10 neutrons. Now, what about ions? Sometimes we have atoms that aren't stable and they gain or lose electrons to become stable. So instead of an atom, what we actually have is an ion. Ions aren't neutral anymore. So what happened with them? Well, what you need to understand is our protons and neutrons are held together by very strong forces inside the nucleus. It's very difficult to mess with the nucleus of a stable atom. So if we're going to interact with the atom and affect its charge, then that means we're going to be playing with the electrons, the substances, or the particles, I should say, that are on the outside of the atom. So let's say we have chlorine 35, and it's got a -1 charge. Well, what has that changed? Well, it's still atomic number 17, so I know protons are 17. 35 minus 17 is the number of neutrons. Remember, we haven't messed with the neutrons. We haven't messed with the nucleus, so protons and neutrons are absolutely no different. Subtract on the side, we get 18. What's different is the electrons. Now remember, an electron is a negatively charged object. As a neutral atom, this had 17 protons and 17 electrons. But now we have a -1 charge. That means we picked up an electron. So instead of 17 electrons, we have actually 18. So we have 17 positives, 18 negatives. Overall, we've got a -1 charge. How about what we call a cation, a positive ion? In this case, we have the calcium 41 cation. Well, remember, we can't mess with the nucleus. So protons and neutrons exactly the same. Atomic number is 20, so we got to have 20 protons. 41 minus 20 is 21, so we have to have 21 neutrons in the nucleus. But the electrons is going to be slightly different. So what's going on with electrons? Now remember, electrons are negatively charged. So if we have a positive charge, that must mean we have more protons, more positive things than negative things. And we have to have two more since it's a +2 charge. So that means our electrons have to be 18. Now remember, it used to be 20 protons, 20 electrons when it was neutral. When we have a +2 charge, that meant we had to lose two of those. And that meant we now only have 18 electrons. So 20 positives, 18 negatives, yes, does cancel to +2. So it works. Next one, we have the oxygen 16 anion, which is called oxide as an anion. Now, once again, we can't mess with the nucleus. So that means protons have to be 8, neutrons 16 minus 8, going to be 8. Now, we used to have 8 protons and 8 electrons, but now we have a -2 charge. Remember, that means we have extra negatives. And how many? Well, it's a 2 negative, so that means we have 2 of them. So we've got a total of 10 electrons. And the last one we're going to try here is the aluminum ion, which is a +3 charge. So once again, can't mess with the nucleus, so we got to have 13 protons, and 24 minus 13, 14 neutrons. Now, a +3 charge means have we gained 3 because it's positive, or have we lost 3? Well, think it through. We used to have 13 and 13. If we have a +3 charge, that means we have to have more positives, which means we have to have less negatives. In fact, we have to have 3 less negatives. So once you write it there, pause a second and think it through. 13 positives, 10 negatives. Yes, that does give me a +3. And that ends our next set of notes over the atom.